So there's a warm-up problem, which I just noticed had a typo, so I had to fix, which is about rewriting integrals. It's what we talked about last time. And normally I'd say, what's the answer? What's the answer? I think I'm going to wait on this one, get a little bit of practice, and then I want to come back and have you try it. So we will come back and revisit this problem later on. Some of you may have already solved it. If you have, and you're like, too easy, actually go ahead and try to finish it. Compute the whole integral. It turns out to be a nice answer. All right, so thought for today. This is a mathematician who wrote this. Said, look, the essence of mathematics is not to make simple things complicated, but to make complicated things simple. And you might say, I don't believe you. I've been in math classes. Everything seems complicated. But there's another quote. If people think mathematics is complicated, it's because they just don't realize how complicated life really is. And but when I think about how to solve problems, essentially in the back of my head is always one overarching mindset. How do I make this simpler? And sometimes problems seem really big. And they can be. But if you say, look, I can't solve the whole problem in one step, and that's okay. Most problems you can't. But can you make it a little simpler? All right, great. Progress. And you do it again, and again, and again. Algebra is really the art of simplifying. And so it's try to make things simple. And as you try to solve problems, don't ask yourself, how can I make this problem more complicated for me? How can I make it simpler for me? All right, now last time, this is a slide we had. I recycled. We talked about a procedure. Now this is the procedure for change of variables. So I should note where it's for, change of variables. And the idea is we're switching, let's say, from x and y to u and v. So there's a change of variables, there's a substitution, there's lots of ways to think about it. Now the first thing is to say, well, what's the substitution? It's almost always given. If it's not given, start saying, what do my inside functions look like? What do my boundary functions look like? Why? Well, because the goal of changing variables is to make things simpler. I mean, everything is trying to say, life is hard enough. Integrals are tough. How can we make it simpler? And so when we're looking for inside functions or looking for boundary lines, that's either simplifying the function we have to integrate or simplifying the bounds we have to work with. The goal here, how can we make things nicer for ourselves? Now, once you know the substitution, every integral has three parts. And what are the parts? Well, usually we think about the function. That's how most people think, oh, I have the function I have to integrate. But you also have the region, or if you like, your bounds, and you have how you're breaking up your region. And so a lot of this discussion says, hey, how do you handle the breaking up your region? So in other words, there's this, as you go from one coordinate system to another coordinate system, or one set of variables to another set of variables, you have some possible local expansion or contraction, and you have to capture that. And that's captured by what's called the Jacobian. So if it is given to you, u and v as functions of x and y, then you set up your matrix of partial derivatives, and you take the determinant, and that'll be dx dy equals du dv. So this tells you how to switch the breaking up part. Now, just remember, the Jacobian is very forgiving. If you mix the columns up, or maybe you write u sub x, u sub y, v sub x, v sub y, you're going to get the same thing. So don't stress too much about remembering exactly what the Jacobian looks like. Just remember it's a bunch of partial derivatives in a somewhat logical way. So what somewhat logical? Notice how you have the one set of variables in the columns, like the u's, the v's. The other variables, the x's and the y's, go in the row. Now, if it's the case that they give you x as a function of u and v and y as a function of u and v, which has happened, no problem. Take a Jacobian, now it's partial derivatives of x and y, and you get dx dy equals that Jacobian du dv. These are tied together insofar as they're telling you how to move back and forth. So if one says expand, the other one says contract, and vice versa. So the product of these is 1. So you can always move things around. One of the things that your book may or may not say, I don't know, I haven't looked in your book for a long time. I don't look in the textbooks. At one point in time, the book would say, suppose they tell you u is a function of x and v, u is a function of x and y, v is a function of x and y, solve for x and y. Why do that? You don't need to. It's more work. And the more work you do, it exposes you to more danger. Be safe. Do as little work as possible. So there are a few errors that can occur. So that's why it's good to know how to do things without doing extra work. Okay, so after you figure out how to break your region, notice you might have to grab part of what you're integrating and absorb it into this Jacobian. So the remainder, when we talk about the remainder, that's what's left over after you account for the Jacobian. And you say, okay, everything else has to go in terms of u and v. And finally, the boundary. Now, for me, the way I like to do the boundary is I say, what's the current boundary look like? Identify your curves. And write them down in terms of x and y. And as you write them down in terms of x and y, you'll say, I can rewrite this expression of x and y into expressions of u and v. And so now that gives us new expressions for our bounding curves. We sketch those curves, and that gives us our new region. Okay, so we have some examples. Let's see. We'll start with this example. Any questions? All right. So, this is from an old exam, an oldie but a goodie. I like this problem. Rewrite the integral from 1 to 2, integral 0 to 2 minus y, of 2y times cosine of x plus y cubed minus 3 times x plus y dx dy. And we're going to do it, they tell us the substitution, because they're nice people. Thank you. U is x plus y, v is y squared. Now here, this is a place where substitution makes sense. Because we look at this integral and we say, would we want to integrate this with respect to x? And our reaction? No. No. Well, what about with respect to y? Even worse. So we don't want to integrate this with respect to x. We don't want to integrate this with respect to y. So we must be using the wrong variables. So hopefully this will help. And you can kind of see why x plus y makes sense. Because you see an x plus y on the inside. So that's a suggestion that x plus y will come into play. Okay, so we start our process. We know our substitution. What comes next? Jacobian. Once you have your substitution, do your Jacobian next. Now, yes, there is some flexibility, but I always recommend Jacobian. Okay, so we're going to take our partial derivatives, u sub x, u sub y, v sub x, v sub y. Take that determinant, take the absolute value of it. Okay, so what is u sub x? 1. U sub y? 1. V sub x? 0. V sub y? 2y. When we take this determinant, what do we end up with? 2y. Now, what does this tell us? What this tells us is if you take 2y dx dy, it equals du dv, or we could say dv du. Doesn't really matter, but the point is that's what's going to happen. So we say, hey, let's look at our function and say we need to pull a 2y to the end. So we're ready to go on to our next part, which is our function. So when we're looking at our function, this 2y is going to move to the back and join with the dx dy. So the function we have to change is just this portion. Cosine x plus y cubed minus 3 times x plus y. All right, so the 2y, that's becoming part of our dx dy. Okay, we have to find some way to rewrite this in terms of u's and v's. Currently it's in terms of x and y's. Can we see any way to rewrite this expression using u's and v's? What is it? Cosine of u to the third, or u cubed? Minus 3u. And we're done. So we've changed our function from something involving x and y to something involving u and v. All right. What's the last part? Bounds, right? Okay, so let's sketch the bounds. Now we're told y goes from 1 to 2. So there's 1 to 2. X goes from 0, which is the y-axis, to the line 2 minus y, which is the line that's going down at this angle. So our region has 3 curves which are bounded. So it's a triangle. All right, so we'll mark our curves. Here we have x equals 2 minus y. Here we have y equals 1. Here we have x equals 0. Those are our current bounding curves. So each one of those curves, we have to rewrite that using our other variables. Okay, so we'll write each one of these down. X equals 0, y equals 1, x equals 2 minus y. Which one do you want to start with? X equals 2 minus y. Bold move. Well, you can add y to both sides. X plus y equals 2. And then you say, I can replace x plus y by u. So that's my new bounding curve. Okay, what about y equals 1? So think about putting y equals 1 up here. Do we see any nice relationships? V equals 1. So when we say a nice relationship, we just want no x's and y's. So if you say, put y equals 1, v equals 1, that has no x's and y. So that becomes our new curve. What about x equals 0? Now that's curious. If we put in x equals 0, our two equations become u equals y, v equals y squared. How can we rewrite that so there's no y? Some people are saying square roots. That's true. However, that sounds complicated. Can we do it without square roots? Yeah, u squared equals v, or v equals u squared. That's our third bounding curve. So now we have our 3 bounding curves. All right. Well, time to sketch. Okay, so we're in our u, v plane. We have v equals u squared. Looks parabola-like. We have v equals 1. And then we have u equals 2. Now where is u equal 2 at? I chose my picture poorly. Let's just say it's 2. So our region is this part right here. Because that's the part which is bounded by all three curves. So you have your v equals 1, your u equals 2, your v equals u squared. So you have this triangle like, it's not quite a triangle because this side is more curved. All right, now we have everything. Okay, so let's write down our new integral. So this will be equal to integral. The 2i dx dy will become a d something. We'll figure out the order in a second. Cosine x plus y cubed minus 3x plus y, well, that's our function. That becomes cosine u cubed minus 3u. Now let's suppose we did want to finish this function, if we theoretically could. Which order of integration should we choose? dv du or du dv? dv du. Hopeless to try to integrate first with respect to u, but maybe, there's a glimmer of hope. Okay, well, staring at our picture, we say, where does u go from? 1 to 2. And then we say, okay, where does v go from? 1 to u squared. All right, so that's the problem. We've actually finished the problem as stated. For fun, do you think we can get an answer? Yeah, let's go ahead and try it. We got space. We got plenty of space. Look at all this luxurious space we have on the side here. Okay, so what's the integral of this? 1 to 2 cosine u cubed minus u v. Evaluate from v equals 1 to v equals u squared. Oops, I forgot my 3 there. There's a 3 there. We'll need that in a second. And du. So this becomes integral 1 to 2 cosine u cubed minus 3u times u squared minus 1 du. Can that be integrated? What if we put u cubed minus 3u as w? What would dw be? 3u squared minus 3 du. Or 1/3 dw is u squared minus 1 du. So, making that substitution, this becomes what? Well, this becomes the integral of, we'll put in 1. 1 minus 3 is minus 2. 2 cubed is 8 minus 6 is 2. I'm updating the bounds. Cosine of w times 1/3 dw. Can we integrate that? Yes. What do you get? 1/3 sine. Evaluate from -2 to 2. Now, because sine is an odd function, you'll get the same thing but different sign if you plug in -2 as if you get +2. So it's double what you get when you plug in 2. So you get 2/3 sine of 2. Now, for fun, I plugged this into Wolfram Alpha, and Wolfram Alpha got the same answer numerically, but it didn't say 2/3 sine 2. It just gave a numerical value. So we're ahead of Wolfram alpha. All right, good. So do you understand the process? Are we ready to now try the multiple choice?
So when you're sketching your UV graphs, how do you know to like put U on the x-axis and V on the y-axis?
So when we're sketching the UV graph, you can put whichever axes you like. I just go sort of, the reason I put U in the quote-unquote x direction is just because it feels right, because U, in terms of the alphabet, becomes before V. But that's literally the only reason why. And that's a silly reason. But because my brain has been trained from years of math teachers. Whether they've been good math teachers or bad math teachers, I don't know. But I'm so used to X being in the horizontal, Y being in the vertical. I say, oh, U, since it comes before V, U should be horizontal, V should be vertical. You'll get the exact same answer if you draw it a different way. Any other questions? Okay, so back to the multiple choice problem. Now the good news is it's multiple choice. So you have a 1 in 5 chance of being correct. So you probably can even figure out what it is pretty quickly. That being said, I want you to try to do the whole process. What's going on? Let's make sure we walk through it. We compute the Jacobian. The Jacobian is 2x. Now, what's different here? What don't we have? We don't have an x. Well, I mean, the 6 we can write as 2 times 3. So it's like, where do we get the x from? The answer, we put it there. So what we can say is like, oh, I can multiply and divide by x. So then I have a 2x that will handle my Jacobian, my change of coordinates from how I break things up. So there's a little x term that needed to be added. And so you say, okay, well, what is x? It's the square root of u. And then, of course, x squared minus y, that's a little bit easier to spot. That becomes a v cubed. The 6 became 3 because I had to pull a 2 off. So from the function, we now know it has to be e. Okay, so, but the bounds we'll work through because we need practice. So the current integral says y goes from -1 to 0, x from 0 to root y plus 1. So that forms a 3-sided shape where one of the sides is a part of a parabola. And namely, it's a parabola x squared minus y equals 1. So our surfaces, our bounding curves, x equals 0. Well, that becomes u equals 0. That's not too bad. Y equals 0. Well, if you put y equals 0, u and v are both the same thing. So u equals v. And then x squared minus y becomes v. So v equals 1. So you get a triangle. So our region is v from 0 to 1, u from 0 to v. Okay, for those of you who saw it quickly, did you go ahead and compute it? I'll tell you the Wolfram alpha answer. See if you can guess it based on what Wolfram alpha said. That's as far as Wolfram alpha got. Any guesses? Pi. And that is the answer. Now, in case you're wondering how do you do it, well, you just remember that Steve loves arctangent. And so what happens if you integrate first with respect to u, you'll get a u to the 1/2 upstairs. Then you do a substitution, w equals v to the 3/2. And then you have your dw. So it becomes a 1 over 1 plus w squared. All right. So there we go. If you got it, good. And if you didn't get it, you'll have more chances. For example, in about a month from now. All right, we're going to mention in passing, we've talked about changing 2D coordinates, but you can do 3D coordinates. So you have some shape in your UVW space, some other shape in your XYZ space. Now, when we say some shape, they're both describing the same thing. It's just the description can be simpler or more complicated. And while I've marked it as a one-way arrow, you can go in both directions as you fix things. Now, what's the basic idea? Well, you say, look, let me take a little tiny thing that's nice and simple, like a nice little parallelogram here. And when you map it over to this other space, it might not be a perfect parallelogram, but it can't be far off. Now, the reason it can't be far off is because functions, when you look at small parts of your function, they behave like flat things. So if you start with a flat thing, like a small parallelogram, it's going to look like a flat thing. Not exactly, but very close. And you say, oh, okay, so it all boils down to understand how do you measure the size of a flat thing. In 2 dimensions, that became what's the area of a parallelogram, which was a determinant. In 3 dimensions, that becomes what's the area of a parallelepiped, which is a determinant. It's one of the things that we talked about when we talked about cross products and dot products. And so the Jacobian is essentially the same thing. It's just a 3x3 collection of partial derivatives, and you take your determinant, and that tells you how to change coordinates. Let's try something, just to convince ourselves that there might be something to this. Do we have an example of a change of coordinate systems? From Cartesian to spherical. Okay, x equals y equals z equals. Do you remember your formulas? We'll start with z. I'll give you a hint. It starts with a rho. In fact, they all start with rho. Rho, cosine phi. Rho, sine phi. In fact, these are both sine phi. What do you need to add to the x? Good. What do you need to add to the y? All right. So we're going to take that big determinant. So let's start with x. The derivative with respect to, we'll start with rho. Sine phi cosine theta. Derivative with respect to phi. Derivative of sine is cosine. Rho cosine phi cosine theta. I should be spacing this out better. Derivative with respect to theta. Minus rho sine phi sine theta. Okay, that's the first set of derivatives. Now I'll do the same thing for the next one. Derivative with respect to rho. Sine phi sine theta. Derivative with respect to phi. Cosine phi sine theta. Derivative with respect to theta. Rho sine phi cosine theta. Last entry, derivative with respect to rho, cosine phi. Derivative with respect to phi, minus rho sine phi. Derivative with respect to theta, 0. So all we have to do is take this 3x3 determinant. Okay, you ready? What's your favorite way to take 3x3 determinants? Diagonals? Plug it into a computer? Cofactor expansion? Okay. We'll do diagonals. Sine phi cosine theta times rho cosine phi sine theta times 0? 0. Nice. Sine phi sine theta minus rho sine phi minus rho sine phi sine theta. Okay, there was a lot of stuff there. Okay, so we had rho squared. We have 3 sines, so sine cubed phi. And then we had sine squared theta. Okay? Dun, dun, dun. Cosine phi times rho cosine phi cosine theta times rho sine phi cosine theta. So we have a rho squared, cosine, cosine, sine. So let's see, that's a cosine squared phi sine phi. And then a cosine squared theta. Did I get that right? Oh, this should be a, this should be a sine squared phi and a cosine phi. There we go. I was worried for a second there. Now everything's great. We're halfway. minus rho sine phi sine theta, rho cosine phi sine theta, cosine phi. We see two rows, rho squared. We see one sine phi, two cosine phis, and two sine theta, so sine squared theta. Okay, so there's that direction. And don't forget the minus sign. And then we have minus. We have two rows. And a sine phi, a sine phi, and a sine phi. That's, oh, sine cubed phi. Interesting. All right. There's a minus sign. I shouldn't forget the minus sign. And then we have a cosine theta and another cosine theta. So that makes a cosine squared theta. Okay, so I think that's it. Did I make any mistakes?
Yeah.
Oh, cool. Which ones did I make mistakes on?
The first one is supposed to be sine cubed.
Which one?
It's supposed to be sine cubed. Being sine phi cubed, which is the first one.
Wait, this one's wrong or this one's wrong?
Top one. That one.
That's supposed to be a sine phi, sine cubed?
Yeah.
Well, let's see. Sine. Oh, sine phi, sine phi, sine. Oh, you're right. It is sine phi. Why did I think there was a cosine phi? I was right the first time. Should have gone with my gut. All right. Well, does it simplify? Let's look at these two terms. They have rho squared in common. What else do they have in common? They have a single sine phi in common. Anything else? No. Oh, that's disappointing. Okay, let's not look at those two terms. Minus, minus here, that makes plus, that makes plus. Hold on. It's just a matter of being patient. I promise you that the punchline's coming. You're very skeptical. I understand your skepticism. All right. Well, let's go ahead and make an observation. Everything has a rho squared, and everything has a sine. Yes? So this is rho squared sine phi. Now, let's look at what's left. We have sine squared phi, sine squared theta, and then down here we have sine squared phi, cosine squared theta, and so that's these two terms, plus from this one we have a cosine squared phi, cosine squared theta, and from this term we have cosine squared phi sine squared theta. Yes. Yeah. You saw the punchline. Okay. Look at this first part here. They both have sine squared phi. If you pull it out, what do you have multiplying by? Sine squared cosine squared, which is 1. So the first term becomes sine squared phi. The second term, well, they both have cosine squared phi. Factor it out. You're left with cosine squared plus sine squared, which is 1. And sine squared phi plus cosine squared phi is 1. So you're left with rho squared sine phi. Have you ever seen that before? Rho sine of phi, right? So what this tells us that dx, dy, dz is equal to rho squared sine phi d rho d phi d theta. So that's where that rho squared sine phi comes from. So it's not just magical, it's a computation. All right, let's see. I think we have time for one more. Okay. So here's a pair of integrals. And we're asked to rewrite. And we have a substitution. So the good news is the substitution's given to us. But it feels like we're going to have to do some work. However, maybe not as much as you think. What do you notice about these two functions? They're the same function. So something fishy is going on here. So let's sketch our region. From 0 to 1, so that's for x, you have x squared and minus x squared. So those are your two curves. So you're going here, that's your first integral. And then you switch from 1 to root 2. You have these curves 2 minus x squared and x squared minus 2. Well, it turns out that 2 minus x squared is an upside down parabola, and it's going to come through and do this. So this is 2 minus x squared. And then x squared minus 2 is coming up, and it's doing this. So this is y equals x squared minus 2. So you're doing that part right there. So that's your region. Now, unfortunately, there's no way to break this up nicely as a single integral. Because if you slice vertically, you have to split into two. If you slice horizontally, you have to split into two. But maybe, after substitution, we don't. Okay, so what comes first? Jacobian. Ux, uy, vx, vy. U sub x? 2x. U sub y? V sub x? V sub y. Take this determinant, what do you get? Minus 2x, subtract 2x. Negative 4x, you take absolute x, you get 4x. And we're like, 4x? Whoa! That's awesome. You have a 4x. Okay, so that 4x dy dx becomes our du dv. Okay, so now we go to our function, say, okay, we have the 4x has been accounted for. E to the x squared minus y over 1 plus x squared plus y squared. That's the part we have to account for. What does the top become? E to the v. What does the bottom become? 1 plus u squared. Okay, the function's done. The last step, the curves. So let's look at our boundary curves. Y equals x squared. What's another way to write y equals x squared? X squared minus y equals 0. What's another way to write x squared minus y equals 0? V equals 0. Y equals minus x squared. That's the same as x squared plus y equals 0, which becomes u equals 0. 2 minus x squared equals y. That's the same as x squared plus y equals 2, which is u equals 2. And x squared minus 2 equals y. That's the same as x squared minus y equals 2, which is v equals 2. Which means, instead of these weird curves, you've got a rectangle. 2 and 2. So our integral becomes, well, 0, 2, 0, 2. Don't even have to think about that. E to the v over 1 plus u squared du dv. And which one of these two would you rather do? The green, yeah. That's why you do substitution. It's a better integral to do. All right. Well, that's it for today.